All right, so this is one of the problems that you guys requested that we talk about. So here we go. Uh, First of all, I'm just going to go ahead and read through the problem. And as I do, pay attention to some of the moves that I make. So it says a radioactive substance decays exponentially. Okay, so instantly this tells me I'm looking at an exponential decay type function. And I'm going to go ahead and I'm going to write that down, like the basic exponential function, right? I could have any base b and any coefficient a. And I'm just going to write this down because it's kind of a template for my thinking. So this is an exponential function. Now, since I also know it's decay, I know that b is going to be less than 1, right? Because if b was 1, we'd end up having a graph that was a straight line. If b is greater than 1, we get with exponential growth. And if b is less than 1, we get exponential decay, right? So it's decaying. And so I know all of that. Okay, so then it says a scientist begins with 100 milligrams. Okay, so that means that's the starting amount. All right, so what does that mean? What does that tell me? Well, if I'm thinking about a graph of this function, I know that the beginning amount, the starting amount, so at time 0, I know I'm looking at 100 milligrams, so up in there. So that's really my y-intercept. Okay, so it begins with 100 milligrams. So really I can see that the point 0, 100 is going to be on my function. All right, let's keep going. Then it says after 35 hours, maybe I should have done this in orange, I was going to flip my colors really quick. It says at 35 hours, we know we have 50 milligrams of the substance. So what that tells me is that actually communicates to me another point, and that other point is 35, comma, 50, right? Because at 35 hours, I have 50 milligrams, so that makes sense. All right. And then what I'm wondering is how many milligrams will remain after 54 hours? So when, I have 54 hours, how many milligrams will they be? So we can keep looking at this as points on a graph, or we can think about these as ordered pairs. We could think about this as a table. Ultimately, and I can think about it as an equation. Ultimately, I'm just looking for how many milligrams at 54 hours. So that's all I really need to know. Okay, so, I wish this would be really easy to figure out, right, if I had an equation. So I wish I had an equation. And that is where I'm going to focus my energies. Now, I could do other things. There are lots of things that I could do. But I'm going to go ahead and just focus on getting an equation because this is one way through. So, I need to know what my lead coefficient is. But I know that that's the y-intercept. I know that, that makes sense for a lot of reasons, and we've looked at those. So really, I have this equation. So it's getting better. And now I still wish I had my base. And while I don't have my base, I do actually have information about x and y, right? I've got this point over here. So what if I just went ahead and used that point? I wonder what that would look like. Maybe I could figure out my base. So I would know that 50 actually equals 100 times my base to the 35th power. Because the power was really my number of hours here. So in this case, x is actually my hours. That's how I'm going to treat it, right? Hours. So then I could just go ahead and I could try to solve for my base. So I could divide both sides by 100, and I would get 1/2 equals the base raised to the 35th. And then I could 35th root this. I could use my calculator to do that. I could raise it to the 1/35th power, right? I kind of like, which is really the 35th root, right? I like thinking about it that way because it's going to be easier for me to type it on my calculator. And then I know that the base is really 1/2 to the 1/35th power. And so I can go ahead and I can figure out that value. And when I do that, what I get the base equals approximately 0.980, 39 is going to be close enough. So that's my base. Now, if I think about what this means, this makes sense because, go back, I had said that the base had to be less than 1 for it to be exponential decay, right? Because that 1 would actually be keeping 100%. But now what I'm actually keeping, if I look at this as a percentage, right, it's telling me that every hour this decays, I keep about 98%, which means I'm losing about 2% an hour. Either way, let's go back and see I wish I had an equation, right? That's what I had wished. Right over here. I wish I had an equation. So we actually have the base now, so I can go ahead and write my equation. I can finish my I wish statement. Here's my equation to the x power. And now, why did I want my equation? Well, I wanted my equation so I could figure out the y value when x was 54 at 54 hours, right? So now I could just go ahead and I can go ahead and figure that out. It'd be nice if I had written this as using function notation. Then I could clearly communicate, that it was the 54th hour. Instead, I didn't do that. That's my fault. So then when I go ahead and I raise this to the 54th power, and then I multiply it by 100, what we end up getting is that y equals 34.3205. I'm going to go ahead and say that. Maybe there's too many sig figs. And if I think about this, what that is that's milligrams, right? Because that was my y value. That was really the milligrams of the substance. And this is after, right, 54 hours. So this is how I could go ahead and tackle that question. And this is just one way. Keep in mind, there are other ways I could have done this. I could have actually gotten creative with my exponents and thinking about half-life if I was really into some of the science stuff. And I could go ahead and show that too. If anybody's interested in writing this as kind of a half-life type equation, let me know.